In 1965, EMD promised railroads a diesel engine so efficient it would revolutionize freight transport. Within 3 years, that same engine was destroying companies from the inside out and costing millions in catastrophic failures nobody saw coming. Late autumn, 1965, LaGrange, Illinois. Electro-Motive Division's engineering headquarters buzzed with confidence that bordered on arrogance. Their latest creation, the SD-45, featured something no production diesel locomotive had ever attempted: a 20-cylinder turbocharged engine generating 3,600 horsepower. The railroad industry's consensus was unanimous. This was the future of American freight transport. If you want to see more videos about old trains that outlasted everything modern, make sure to subscribe so you never miss another video. Every major railroad executive from Chicago to Los Angeles studied EMD's specifications with growing excitement. The SD-45's 645 E3 engine promised 15% more power than existing locomotives while consuming less fuel per ton-mile. In an industry where profit margins lived and died on fuel efficiency, this wasn't just an improvement, it was salvation wrapped in steel and chrome. Southern Pacific's procurement team had already calculated the numbers. Replacing 3 older locomotives with 2 SD-45s would cut crew costs, reduce maintenance facilities, and deliver freight faster across their mountainous western routes. Union Pacific's engineers projected fuel savings that could reach $2 million annually across their fleet. Santa Fe Railway saw an opportunity to dominate transcontinental freight by operating the most powerful locomotives in North America. EMD's sales literature painted a compelling picture backed by dyno testing data that seemed irrefutable. The 20-cylinder engine's turbocharger forced air into combustion chambers with unprecedented pressure, extracting maximum energy from every gallon of diesel fuel. Advanced fuel injection systems atomized diesel into microscopic particles for complete combustion. The engine's increased displacement meant more power strokes per revolution than conventional 16-cylinder designs. Traditional railroad wisdom suggested caution when adopting unproven technology. Locomotives operated in harsh environments spanning Arctic winters to desert summers, pulling loads that stressed every mechanical component to its limits. Conservative engineers at General Electric warned that adding 4 cylinders and a turbocharger created complexity that field maintenance crews might struggle to manage. But EMD's reputation seemed to eliminate such concerns. The company had dominated American diesel locomotive manufacturing since the 1930s, building reliable engines that transformed railroading from steam to diesel. Their 16-cylinder 645 engine had proven bulletproof across thousands of locomotives operating in every climate imaginable. Adding 4 cylinders and a turbocharger seemed like logical evolution rather than dangerous. Experimentation. The SD-45's debut at the 1965 Railway Progress Institute showcase in Chicago drew crowds that overwhelmed EMD's exhibition space. Railroad executives examined the massive engine like prospectors who had discovered gold. Mechanical engineers studied the turbocharger installation with admiration. Financial officers calculated purchase orders that would transform their fleets from outdated workhorses into cutting-edge profit generators. Orders flooded EMD's sales department before the first production locomotive left the factory. Southern Pacific committed to 150 units. Union Pacific ordered 96. Santa Fe Railway placed orders for 5. Even smaller regional carriers like Cotton Belt and Erie-Lackawanna invested in the technology that promised to level the competitive playing field against larger competitors. By December 1965, EMD had sold over 400 SD-45 locomotives totaling more than $200 million in orders. The railroad industry's future seemed clear: more power, better efficiency, reduced operating costs. Nobody questioned whether pushing diesel locomotive technology this far might exact costs that financial projections hadn't considered. What could possibly go wrong when an engine that looked perfect on paper met the brutal reality of 24/7 railroad operations across an entire continent? The SD-45's 20-cylinder configuration represented EMD's boldest engineering decision since abandoning steam locomotives. Traditional 16-cylinder engines had established a proven balance between power output and mechanical reliability. Adding 4 cylinders and turbocharging created an engine operating at the absolute edge of metallurgical and thermodynamic limits. EMD's chief engineer, Harold Hamilton, understood the risks but believed modern materials science had solved the problems that plagued earlier high-output designs. The 645E3 engine used enhanced steel alloys in crankshafts designed to handle torsional stresses that would have shattered earlier metals. Piston rings incorporated ceramic coatings that reduced friction while withstanding combustion temperatures exceeding 2,000 degrees Fahrenheit. The turbocharger installation required precision engineering that pushed manufacturing tolerances to their limits. The Roots blower supercharger forced compressed air into cylinders at pressures carefully calculated to maximize combustion efficiency without creating detonation that could destroy pistons instantly. Intercoolers reduced intake air temperature to increase oxygen density, squeezing maximum power from each combustion cycle. But the 20-cylinder configuration created mechanical challenges that 16-cylinder engines never faced. The crankshaft stretched over 18 feet long, flexing microscopically with each power stroke from 20 pistons firing in carefully orchestrated sequence. Harmonics vibrated through the engine block at frequencies that could fatigue metal over thousands of operating hours. The turbocharger operated at rotational speeds exceeding 20,000 RPM, spinning with such velocity that bearing failure meant catastrophic destruction. Cooling systems struggled with thermal loads that exceeded anything EMD had previously managed. 20 cylinders generated heat that required radiator capacity 25% larger than 16-cylinder engines. Water pumps circulated. Coolant at 400 gallons per minute through passages engineered to prevent hotspots that could warp cylinder heads. Even small cooling system failures could cascade into engine destruction within minutes. Lubrication presented equally daunting challenges. The engine consumed oil at rates that surprised even EMD's engineers during extended testing. Turbocharger bearings operated at temperatures and speeds that degraded oil rapidly. Piston rings scraped cylinder walls with friction that contaminated lubricant with metal particles and combustion byproducts. Oil filters required replacement intervals 30% shorter than 16-cylinder engines. Field maintenance complexity increased exponentially. Railroad shop crews accustomed to servicing proven 16-cylinder engines faced turbocharger systems requiring specialized tools and diagnostic equipment many facilities didn't possess. Replacing a single failed cylinder required disturbing adjacent components in ways that 16-cylinder engines' more accessible layouts didn't demand. EMD's testing program had subjected prototype engines to thousands of hours under controlled conditions that simulated railroad operations. Dynamometer cells measured power output. Climate chambers replicated temperature extremes. Fuel quality tests used samples representing the diesel fuel spectrum railroads purchased, but laboratory testing couldn't replicate the brutal randomness of actual service where locomotives idled for hours in sub-zero temperatures, then accelerated to full power pulling 10,000-ton trains up mountain grades. The first production SD45 locomotives rolled from EMD's LaGrange facility in early 1966, destined for Southern Pacific's Roseville, California yard. Painted in SP's distinctive gray and scarlet livery, the locomotives represented $3.2 million in capital investment that Southern Pacific's Board of Directors had approved based on EMD's efficiency projections and reliability promises. Could engines designed to perfection in Kishit? Climate-controlled laboratories survived the chaos of daily railroad operations where nothing went according to plan. Spring 1966 brought the SD45's operational debut across the American Southwest, with results that initially seemed to vindicate every efficiency claim EMD had made. Southern Pacific's first units hauling freight between Roseville and Sparks delivered exactly the performance specifications had promised. 3,600 horsepower moving tonnage up Sierra Nevada grades that older locomotives handled only with helper units. Union Pacific's mechanical department reported fuel consumption figures matching EMD's projections during the first 90 days of operation. The locomotives pulled 100-car freight trains across Wyoming's high plains at speeds that reduced transit times by hours compared to older power. Dispatchers celebrated reduced delays. Customers received shipments faster. Financial officers began calculating returns on investment that seemed to justify the premium prices SD45s commanded. Santa Fe Railway's SD45s transformed their transcontinental freight operations through California's Cajon Pass, where steep grades had always demanded multiple locomotives. Two SD-45s could handle trains that previously required three older units, cutting crew costs and improving schedule reliability. Mechanical inspectors reported the new locomotives passing inspection points without the oil leaks and minor failures that plagued aging equipment. Railroad trade publications featured glowing articles about the SD-45's impact. Trains Magazine's March 1966 issue showcased Southern Pacific's new fleet with color photography that captured the locomotive's imposing presence. Railway Age published technical analyses praising EMD's engineering achievement. Industry conferences featured presentations detailing fuel savings and operational improvements that seemed to validate every railroad's decision to invest in the technology. EMD's order book continued expanding as railroads unwilling to risk obsolescence joined the SD-45 revolution. Chicago and Northwestern ordered 42 units for their coal hauling operations. Missouri Pacific committed to 35 locomotives for freight service through the Southwest. Even Canadian National Railway purchased SD-45s for service across the Canadian prairies, where extreme winter temperatures tested equipment to destruction. The financial commitment reached staggering proportions by mid-1966. Railroads had collectively ordered over 700 SD-45 locomotives, representing more than $350 million in capital investment. Banks financed purchases based on projected fuel savings and operational improvements that seemed mathematically certain. Railroad executives presented SD-45 acquisitions to shareholders as strategic necessities rather than optional equipment upgrades. But subtle warning signs emerged that most railroads dismissed as expected teething problems with new technology. Southern Pacific's Roseville Maintenance Facility began tracking turbocharger failures occurring after 60,000 miles, sooner than EMD's specifications predicted. Union Pacific's shops noticed oil consumption rates creeping upward as engines accumulated operating hours. Santa Fe's mechanical teams reported cooling system issues on locomotives operating in Arizona's summer heat. EMD's service bulletins addressed these early failures with technical modifications and revised maintenance procedures that seemed routine for new locomotive models. The company's field representatives worked with railroad mechanical departments to fine-tune operating procedures and maintenance intervals. Most railroads accepted these adjustments as normal refinements, rather than indicators of fundamental design problems. The industry's optimism remained unshaken through summer 1966. Railroads had invested too heavily to consider that EMD's efficiency promises might rest on engineering assumptions that daily operations would prove catastrophically wrong. The SD-45's real test was just beginning, and the results would shatter decades of trust between railroads and their primary locomotive supplier. How long could locomotives operating at the absolute edge of mechanical limits survive before the cracks became catastrophic failures nobody could ignore? Late 1966 marked the moment when isolated SD-45 problems transformed into systematic failures that terrified railroad mechanical departments across North America. Southern Pacific's Sacramento shops documented their first catastrophic turbocharger failure in November when Unit 8914 suffered complete bearing disintegration at speed, spraying metal shrapnel through the engine compartment. The repair bill exceeded $85,000 for a locomotive only 8 months old. Union Pacific's North Platte facility reported bearing failures in main crankshafts occurring at mileages far below EMD's predicted service intervals. The 18-foot crankshafts flexed under power loads in ways that created stress concentrations where bearing journals met the crankshaft body. Metal fatigue propagated microscopic cracks that suddenly fractured catastrophically, destroying engines that required complete rebuilds, costing over $200,000 per unit. The crankshaft problems revealed fundamental miscalculations in EMD's engineering. 20 cylinders created torsional vibrations that resonated through the crankshaft at specific RPM ranges. Locomotives operating in these critical zones experienced metal fatigue that accumulated invisibly until sudden failure left trains stranded on main lines blocking traffic for hours while rescue locomotives arrived. Santa Fe Railway's Barstow shops tracked cooling system failures that occurred with alarming regularity. The engine's massive heat generation overwhelmed radiator capacity during sustained high-power operation in desert conditions. Coolant temperatures climbed past safe limits, warping cylinder heads and causing head gasket failures that dumped coolant into combustion chambers. Locomotives suffered hydrolock when pistons tried compressing liquid coolant instead of air, bending connecting rods with forces exceeding 100,000 pounds. The turbocharger proved especially vulnerable to operating conditions that laboratory testing had failed to replicate. Turbochargers spinning at 20,000 RPM required continuous oil flow for bearing lubrication and cooling. But locomotive idling periods, sometimes hours at classification yards, allowed turbocharger temperatures to drop. Sudden acceleration to full power forced cold oil through hot bearing surfaces, creating thermal shock that cracked housings and seized bearings. Oil consumption became an epidemic that bewildered mechanical departments expecting fuel efficiency, not voracious lubricant consumption. SD45s consumed oil at rates approaching 1 gallon every 80 miles during hard service, nearly triple what 16-cylinder engines required. Piston rings designed for high compression couldn't seal effectively across the massive bore, allowing combustion pressure to force oil into combustion chambers where it burned away as expensive blue smoke. Railroad maintenance budgets hemorrhaged money attempting to keep SD45 fleets operational. Southern Pacific's 1967 locomotive maintenance costs exceeded projections by $4.3 million, with SD45 repairs consuming disproportionate resources. Union Pacific's mechanical department pleaded with management to stop accepting new SD45 deliveries until EMD solved reliability problems. Santa Fe Railway began parking some SD45s rather than spending money maintaining locomotives that failed repeatedly. EMD responded with engineering modifications and revised component specifications, but the fixes addressed symptoms rather than fundamental design flaws. Upgraded turbochargers failed slightly less frequently. Revised piston rings reduced oil consumption marginally. Modified cooling systems delayed rather than prevented overheating failures. The railroad industry's investment in SD45 technology had become a financial trap. Railroads owned hundreds of locomotives too expensive to abandon, but too unreliable to operate profitably. The efficiency claims that drove purchase decisions had transformed into operational nightmares where maintenance costs exceeded the fuel savings EMD had promised. Could EMD rescue the SD45's reputation before railroads abandoned the model entirely, or had the engineering gamble already failed too catastrophically for any fix to restore trust? By 1968, the SD45 crisis had escalated from mechanical problems into a corporate catastrophe affecting the entire North American railroad industry. Southern Pacific's board of directors demanded explanations for maintenance budgets spiraling 4% over projections, while SD45s sat disabled in shops awaiting parts that EMD couldn't supply fast enough. Union Pacific's executive committee questioned whether their $150 million SD45 investment represented the worst capital allocation decision in the company's century-long history. The financial damage extended beyond direct maintenance costs. Disabled SD45s forced railroads to maintain older locomotive fleets they had planned to retire, doubling capital equipment expenses. When SD45s failed en route, railroads incurred penalties for late freight deliveries, damaging customer relationships built over decades. Classification yards kept rescue locomotives positioned to retrieve failed SD45s, wasting capacity that should have hauled revenue. Freight. Santa Fe Railway's mechanical superintendent submitted a devastating analysis to management, calculating that SD45s cost 37% more per mile to operate than the older GP40 locomotives EMD claimed the SD45s would replace. Fuel savings evaporated when accounting for oil consumption, increased maintenance labor, and the premium prices railroads paid for parts EMD rushed through production to address field failures. Railroad mechanical departments discovered EMD's testing protocols had fundamentally miscalculated field service conditions. Laboratory dynamometer testing ran engines at steady power settings for measured intervals. But actual railroad operations meant locomotives idled for hours, accelerated violently to full power, then operated under varying loads as trains navigated grades and curves. The thermal cycling destroyed components engineered for steady-state operation EMD's testing had simulated. The turbocharger failures proved especially intractable because the failure mechanism involved metallurgical factors that simple design changes couldn't address. Turbocharger shafts operated in bearing surfaces with clearances measured in thousandths of inches. Oil contamination from the engine's excessive consumption introduced abrasive particles that scored bearing surfaces. Once scored, bearings failed rapidly, destroying turbochargers that cost $45,000 to replace plus labor expenses for removal and installation. Legal teams at major railroads began reviewing purchase contracts to determine whether EMD's efficiency claims constituted misrepresentation that might justify warranty claims beyond standard coverage. Southern Pacific's attorneys drafted letters demanding EMD assume financial responsibility for SD-45 maintenance costs exceeding the levels projected during purchase negotiations. Union Pacific threatened litigation if EMD didn't provide immediate solutions to crankshaft failures that had destroyed 14 engines requiring complete rebuilds. EMD's response combined technical support with legal maneuvering that infuriated railroad executives. The company provided upgraded components at no charge while simultaneously arguing that railroad operating practices and fuel quality contributed to failures in ways that voided warranty coverage. Field representatives suggested that railroad maintenance procedures inadequately serviced the sophisticated technology the SD-45 represented. Smaller railroads like Cotton Belt and Erie-Lackawanna faced existential crises as SD-45 maintenance costs consumed budgets that couldn't absorb losses major carriers could tolerate temporarily. Cotton Belt considered selling their entire SD-45 fleet at devastating losses rather than continuing to operate locomotives that bankrupted maintenance budgets. Erie-Lackawanna's precarious finances deteriorated further as SD-45 problems added operational chaos to financial difficulties that would eventually force the railroad into bankruptcy. Industry publications that had celebrated the SD-45's debut now published critical analyses questioning whether EMD had rushed the design to market without adequate validation testing. Railway Age's October 1968 editorial suggested the SD-45 represented corporate hubris, where marketing considerations had overwhelmed engineering prudence. Would EMD acknowledge fundamental design flaws and recall the model? Or would railroads be forced to absorb losses from the worst locomotive investment in modern railroad history? The SD-45's commercial failure triggered consequences that reverberated through the railroad equipment manufacturing industry for decades. By 1969, new SD-45 orders had collapsed to fewer than 20 units as railroads, unwilling to risk additional capital on the troubled model, pursued alternative locomotives. EMD's market dominance faced legitimate threat for the first time since the 1940s when General Electric's competing U-30C model captured market share from railroads desperate for reliable high-horsepower alternatives. Southern Pacific implemented the industry's most aggressive SD-45 modification program, investing $19 million to downrate 150 locomotives from 20 cylinders to 16 by physically removing cylinder assemblies and reconfiguring fuel systems. The SD-45-2 conversions sacrificed the horsepower that had justified purchase costs but created locomotives reliable enough to operate profitably. The modifications proved that EMD's 16-cylinder 645 engine design was sound. The 20-cylinder configuration had simply pushed the architecture beyond sustainable limits. Union Pacific pursued a different strategy, concentrating SD-45s on specific routes where shorter distances between major maintenance facilities allowed intensive monitoring. Locomotives operated under restricted protocols that limited sustained high-power operation, reducing failures, but also negating the efficiency advantages that had justified their purchase. UP's mechanical department developed expertise managing SD-45 peculiarities that other railroads couldn't replicate, allowing UP to extract marginal value from their troubled fleet. Santa Fe Railway began retiring SD-45s by 1974. Selling units to short-line railroads and leasing companies at prices representing 40-cent dollars on original investment. Some locomotives accumulated fewer than 400,000 miles before retirement, a fraction of the 2 million-mile service life railroads expected from quality locomotives. The financial write-offs. damaged Santa Fe's quarterly earnings and forced management to explain to shareholders how sophisticated engineering analysis had so completely miscalculated operational reality. The failure's technical lessons reshaped locomotive design philosophy across the industry. EMD's subsequent SD40 model reverted to a proven 16-cylinder configuration with conservative turbocharging that prioritized reliability over maximum horsepower. General Electric's engineers studied SD45 failures intensively, incorporating lessons about metallurgical limits and thermal management into their FDL-16 engine design that would eventually capture majority market share from EMD. Railroad procurement practices transformed as mechanical departments demanded extended field testing before accepting new locomotive models. The SD45 disaster proved that manufacturer testing could not replicate the brutal randomness of actual operations where locomotives faced combinations of temperature extremes, fuel quality, variations, and operating profiles that laboratory conditions couldn't simulate. Railroads insisted on pilot programs where small fleets operated for 18 months before committing to fleet-scale orders. The financial damage proved difficult to quantify precisely, but certainly exceeded $500 million industry-wide when accounting for excess maintenance costs, lost productivity from disabled locomotives, legal expenses, and the capital destruction from premature retirements. Southern Pacific alone absorbed losses exceeding $80 million, a staggering sum that could have purchased 150 proven locomotives if management had resisted EMD's efficiency promises. By 1980, most SD45s had been retired, rebuilt to 16-cylinder configurations, or relegated to secondary service on short lines where their maintenance demands could be managed through intensive care. The model that promised to revolutionize railroad efficiency had instead proven that even sophisticated engineering could catastrophically misjudge the difference between theoretical performance and operational reality. Could the railroad industry have avoided the SD45 disaster if executives had questioned efficiency claims that seemed too good to be true, or did corporate pride and competitive pressure make the mistake inevitable?